I'm going to start the talk. It's as you already know, it's about oak, and it was done in Yahoo Research, currently Verizon Media Research, and we have work on it with almost our entire team. So I'm going to show you. Let us start. Okay, so oak is actually abbreviation for off-heap allocated keys. And I'm going to really briefly explain what it is. So it's actually key value map. It's in memory. It's concurrent, of course, highly scalable. And it was designed for big data. Big data meaning above 50, 100 gigabyte and more. Currently, we have machines that support such RAM. It's written in Java, and maybe if you try to use 100 gigabyte and more with any Java collection, it's going to be hard. But oak actually doesn't cause any garbage collection, JVM, Java Virtual Machine garbage collection activity. For it has better performance, and it uses much less memory. Okay, what are good news? This is open source library. Here you can see the link, and we'll be happy if you go and check it after the lecture. Okay, so let's speak about Off-heap. Why Off-heap? So what do you see here? It's logos of many open sources project databases. And what is common among them that all of them are using Off-heap as a place where to put their data. Okay, so we are going to understand this much more detail, but at least we can say all of the rest are doing the same. All of the rest are using Off-heap, but we are using it a bit different, so you're going to see it soon. So just as motivation, let's say that I have a big machine with big RAM, and what do you think I can do with 128 gigabyte of RAM? Okay, let's assume I want just to push some data there. So I'm going to push pieces of data to ingest 1 kilobyte at a time, and I'm going to measure the throughput, how fast I can do those insertions. Okay, so this is the experiment that I'm going to do with a concurrent skip list map, the famous skip list map of Java. It's log-free, it's used widely, very, very widely. So on axis X, as I said, we are going to see gigabytes, how much I can push until I get to the out of memory exception. On an axis Y, you are going to see the throughput of single thread. Okay, we are not going to do anything concurrently, just to see how it works. And usually I would ask audience to say till where do you think it's going to end, but currently we're just going to answer it. I'm going to answer it myself. So here's the graph. As you can see, it's representation of concurrent skip list map. It's UGC, and we are stopping at 60 gigabyte. Okay, so out of 128, you have almost just half. Okay, this is not so good memory utilization, and so where actually the resources gone? Okay, so mostly you have internal GC structures themselves. Okay, and actually I want you to pay attention. I'm going back and see that the throughput is decreasing. Yeah, you see what we start about 200 kilo operations per second, and as much as we are hitting the headroom with memory, the throughput is less and less. Okay. So again, I'm going to say that the GC structure are requiring memory, and object headers are heavily using your memory. Maybe you're of course familiar with that. Each Java object has about 24, maybe more bytes of header. Okay. And of course, as also you know, GC algorithm takes CPU cycles. Therefore, you saw the degradation of the throughput. And But of course, we do need this GC. I'm honestly impressed with the GC performance now, relatively for how it was a couple of years ago and before. And it's important for a programming experience that you just doesn't care about the memory where it goes, so just collect it somehow behind the skins. So in Oak, we try to give the same programming experience to the user. So we do not rely on GC, but we do reuse the memory. Okay, so here I'm going to speak a bit about the background. So just to understand what the off-heap memory is, because this name off-heap is actually confusing. Let's think about process address space. You probably know that we have processes in the operation system, and each process is assigned a virtual address space, which is because it's virtual, it assumes like all of it is related to one process. Okay, so if we're looking on some Java process address space, there are areas in the memory who are not related to our discussion, and there is some area allocated for JVM, okay, and managed by JVM. Anything written there is written according to JVM algorithms. And there are metadata, of course, on this metadata. It's managed by JVM machine. And there are more memory in the process address space that you can allocate. You can take it just directly from operation system, from OS. Okay, and it's not managed by JVM. Okay, therefore, if you look on the process address space, they are located in the same place. And the naming of heap and on heap and off heap, it's a bit confusing, but it's maybe we can say off Java heap. Okay. And if you want to use off heap, then how are you going to do it? Inside the Java program, you're going to allocate direct byte buffer, which the object itself is going to be on the heap, and it's going to reference with its address to the bytes, to the just stream of bytes in the off-heap memory. Okay. So working with off-heap is a bit challenging. Of course, we do it because we have benefits of it. So what are the benefits? We have no JVM cost. This is the biggest benefit. We don't have object headers, but how do we write there? We actually just we just have stream of bytes. We don't have objects at all. Therefore, we also don't have object headers. Okay. We have quick access, actually. When you do access directly to the off-heap, to the memory related to OS, it just makes it faster because there are no GC algorithms running in the background. Okay, but how to reuse memory is a big question when you have off-heap. And also big question in the performance-wise is the meaning that you need to serialize and deserialize the objects. And of course, the concurrency. How do you access off-heap concurrently? Okay, so we're going to see other answers to all those questions, but just to summarize the contribution of Oak. So again, what it is, it's keys and values taken off-heap. That's the main purpose. Okay, on top of it, you need to think again how you design the data structure, the well-known data structure, which is map, in order to support performance and concurrency and all what you need off-heap. Okay. In addition, when you have those data serialized off-heap, the question is how do you access it? Because the normal concurrent navigable map API of Java requires objects. And if you are going to create objects, serialize them and deserialize them, it's going to cost you, of course, CPU cycles. And therefore, we design new API, which I'm going to talk about, to work with zero copy, without copying from off-heap to on-heap. Of course, concurrency is a bit different because the entire structure is a bit different. And we present the interesting two-way scans. Generally, if you think about concurrent skip list, all the arrows are to the one direction. You can travel only one direction in the skip list. And if you want to go backward, you either need how backward scan is implemented in concurrent skip list, you just go log n steps backward, okay, which is, of course, not so bad. It's a bad performance. And we will show you how do we do the scans backward without need to traverse really against the arrows or to add arrows backward, because if you add the linkage backward, it's going to be hard to make it concurrent again. Okay, so this is what we contribute with our project, and what we get out of that is a data structure which is really lean in memory. We have just 3% overhead on top of the raw data, and we have fast performance. You're going to see it. Its scale is much better. The more threads you add, the better performance is, which is not always the case. We have real world deploy. We have open source library. So those are outcomes of our project. Okay, and if you want to see the result with Oak, remember the graph we saw in the beginning. So here you see we are reaching about 115 gigabytes, much longer, and the throughput is better than concurrent skip list path for Java. Okay, so let's dive in and see how data is organized in Oak. Okay, but first, I would like to explain our design approach, because we learned a lot when we work with Off-heap, and we have some design points based on which we are going to present the data organization. Okay, so first, we want to have, of course, as less metadata as possible. First of all, our metadata is on heap and data is off heap, so we want to use as less on heap as possible in order not to make GC working. And of course, we will want to have as less overhead in general. Okay, so the red color represents on heap, it's going to be small, and blue color represents off heap, it's going to be big. Okay, and again, Java objects, we want to have them as less as possible, but there is a twist that they're going to explain in the end. But in generally speaking, yes, we want as less objects because we don't want to have the headers floating around. So if you're thinking about any data structure, which is kind of graph pointing from one point to the other point, so we would like to eliminate that. Even if you have Java style array, when you have an array of heads pointing to each object, each object is again going to have header. You don't want that. So what we do use is an array of primitives, in our case integers, which do not have any objects, and we just interpret the integers as some kind of object that they're going to explain later. Okay, other point is maintenance in batches. So of course the allocation of heap is a bit slow, of off-heap, I'm sorry. Allocation of off-heap memory is a bit slow. Therefore, we allocate it once and then use it again and again. And even managing of the on-heap memory, we do it in chunks, where we keep the location. Access is locality based, and therefore we enjoy a cache oblivious algorithm, and we are going to see the results in the performance. Okay, so again, we try to eliminate the copy. The values for big data are big, and therefore we don't want to copy them off heap and on heap again. Therefore, we create a new API. We let user, in order not to create the object for user, we let user access our raw data, where we keep all the data, of course, but we are on guard, and we have the objects in between the user and our data in order to make it more safer. Okay. And again, we are trying to eliminate as much ephemeral objects as possible. When, for example, you traverse data, you can create some helping objects, some translating objects, some whatever you may think about. But we have one small case about the NUMA architecture. When you have different accesses from different places in the memory, recall the NUMA architecture means a non-uniform memory access. So you have cores and memories in different locations, and there can be access to the same core memory, and which is fast. And if a thread needs to access other core memory, is going to be slow. So, for example, if you allocate an array for some kind of thread, next time if you keep this array, it can be accessed from other thread which is far away from this one. So in this case, you maybe do not want to keep objects alive. Even in this case, we have measurement that it's going to be better for you to allocate it once again. Okay, so going to the Oak data organization. So the building block of Oak is chunk. Okay, what is chunk? Chunk is responsible for a range of keys, and keys in our case are immutable, they are unique, and they have variable size. Because they have variable size and we do not keep them in, actually chunk is on heap, we do not keep keys on heap, we have just entries. Inside chunk we have entries which are represented as integer array. On top of it, we just cut a couple of integers and we say this is an entry that I need. What is entry? Entry is actually a reference to key and to value, which are located off heap. But they themselves are on array, but connected with the linked list. Okay, so you see here those white arrows. This is the linked list. And the chunk is, as I said, responsible for some range of keys. The chunk is limited in memory. It has an array of entries. So it can become full at some point. When chunk becomes full, we split it in two chunks, and then again and again. So each chunk is created from other chunk, except of the real first one. So when we create chunk from old full chunk, we create two chunks half full. We organize the entries in such a way that they are ordered. So linked list is pointing just on the next entry in the array. And then the next half is going to be inserted while chunk is alive. It's not going to be ordered, but the linked list on top of the array is going to keep the order. Okay. So here you can see that half of the chunk is actually, of the entry is actually ordered, and the linkage is subsequent. And why do we do this? Why it's important for us? This is because on this part of chunk, where we have fixed size entries and they are ordered, we can allow ourselves to do binary search, which is a huge advantage, because otherwise we will need to traverse the linked list in a sequential way, which is big difference in the performance, as you know. Okay, so we have, of course, multiple chunks that have ranges of all of the keys in the spectrum. And of course, we do not want to have accessing the chunk which are connected in the linked list of chunks. We have index on top of chunks, where you give this index a key, and this index gives you back chunk where you need to look in order to find whether this key exists or doesn't exist. Okay, this is all that we have on heap. Other than that, we have blocks in the off heap, which are pre-allocated, as we said. And this block may have all the keys and the values, and entries are actually referencing some key and some value. Okay, in order to access keys and values, we define ephemeral objects which are named Oak buffers. Oak buffers can be for read and for write, so therefore Oak R buffer or Oak W buffer. And when the user needs to keep oak buffer or any data, and we allow not to access it through object. We give a user just oak buffer, and here's the buffer. Just use get char, get in, get whatever, and access the data that you need. Okay. And you see next to each value, we have header. There's a H, there's letter H next to each value. This is the header where we keep one machine word for our metadata, which is 64 bits. We keep this for synchronization and for deletion. And I'm going to explain it a little bit in detail later. Okay. So I would like now to turn to the questions that may come from the audience. And maybe, is it clear? Is it not clear? Maybe you have some questions to ask.
I have my personal question. Have you considered moving metadata to off-heap as well?
Actually, it's possible to move chunks to the off-heap because they're actually array of integers, and it's not hard to make it. But we didn't measure this possibility. We didn't do the evaluation stage of this idea. Like, it's possible that it's going to, of course, it's going to have less metadata, but Oak has in general very little metadata. It's about 3% of the on top of the raw data. Therefore, it's not the highest, let's say, the highest idea that we want to pursue as soon as possible.
Okay. Well, also I have a question about off-heap. How do you manage off-heap? There are not many options for a Java developer to go off-heap. For example, you can use JNI calls, or you can, for example, use direct byte buffers, or maybe use some dark techniques like unsafe. So what is the solution for Oak?
Yeah, in Oak, we use unsafe, and we found it the best solution in the manner of performance-wise. And but of course, moving to JDK 11, it's a bit problem for us, but it's not actually, it's not a problem. There's a solution for any unsafe anything that was suggested with unsafe. It's going to be resolved in JDK 11, not via unsafe. And I'm going to talk about closer to the end of the lecture. I'm going to talk about how we use Oak. For us, we found the best ways to allocate direct byte buffers through allocate direct from OS actually, and then we keep them entirely as blocks, as block pool. And the managing of the byte buffers is going to be through put long, and whatever, get long, which is not unsafe, which is part of direct byte buffer interface. Direct byte buffer can give you also access, a stronger address interface, and address and offset, and then you can manage it this way. And in order to synchronize over off-heap, we do use unsafe capabilities, and we have solution how to do it in JDK 11 as well. So yeah.
Okay, it makes sense. Well, and there is a question from the chat. The chat is interested in what kind of serialization and deserialization is used to put the objects to off-heap.
We do suggest serialization. First of all, we have a kind of interface, Oak serializer and Oak deserializer, where user can implement any we assume that user have the best knowledge about the keys and values objects that are used inside Oak. Therefore, they can, the best who can write the serializer or deserializer is the user itself. Therefore, we have such an interface. We do provide a serializer and deserializer for a simple object like integer long strings and things like that. And so you can just use it if your data, for example, are strings. And for complex objects, we require user to write serializer, deserializer. And we consider using some general code solutions like crypto, but currently we do not embed such a solution. So bottom line, a user is required to create serializer and deserializer.
Okay, so so far no more questions. I believe we can proceed with the talk, and we can ask questions later.
Okay. Thank you very much. Thanks. Let's continue. Okay, so I'm going to speak a bit about our API. So we introduced zero copy API for OakMap. OakMap supports also the concurrent navigable map API, but we suggest to use zero copy. And for example, when you have a get from a concurrent navigable map, you assume giving object K, and you assume you're getting back object V. Okay, if we are going to do it, we will need to just, for example, of course, in concurrent navigable map, in concurrent skip list of Java, it's easy to return any V. Value of object V is already existing, just return whatever you have, and no copy is required. But for all case, we will need to create an object, and what we suggest in order not to create the object is to use OCR buffer. It's going to be ephemeral object for this thread. Okay, then you can access the value in its serialized way, which was serialized actually by the user themselves. And then if you serialize that, then you maybe know how to access it in its serialized way. It's going to be much faster. And now about the scanning. Okay, scans is usually an iterator, iterator over a set, for example, key set. And again, when you have some on-heap data structure, it's easy just to return an object. But we suggest to use key stream set. What does it mean? That we return kind of stream iterator. Why? Because when you do even zero copy iterator, so returning buffers, you need to create this Oak buffer anytime you do next. And next is actually a really, really small operation. It's kind of a couple of machine operations, for example, concurrent skip list map. And if we are going to create a new object anytime you do next, it just decreases the performance. But maybe you don't need to create a new object. You anyway are not going to access any object back. Right, then the stream view is what you need. We have the same object, just reference anytime to the new buffer. Okay, we are going to see the relation results, and we're going to see how much better it is. So once less, what we introduce is put if absent, compute if present. This is a kind of a new API that means that you give me a key, and you are yourself unsure whether this key exists in the structure or not. And so if it exists, you want to compute it. What does it mean to compute? It means to update the value. Any update of any value is going through compute interface, and you're going to give me a compute function how to change this value from what it was to anything you want. And if it actually wasn't in the set, then we are going to use put if absent and to put it in the set. But the most important thing that we do it atomically. Therefore, till the end of operation, it's either exist or doesn't exist. And according to that, we are going to compute or to put. Okay, this wasn't possible to do with concurrent skip list map, because it was possible to do, but not concurrent, not atomically. I'm sorry. Okay, I'm going to really quickly speak about concurrency without much details. What is important for me to mention is separation of concerns. So we have here data structure itself concurrent, and we have here the data, which is also concurrently accessed. Okay, so first we speak about the data structure, our internal data structure, which is lock-free. The concurrency here is lock-free. We don't have locks. We use concurrent solve operation on heap metadata. And this is how we manage the internal puts and delete coming simultaneously and updating the data structure itself. On the other hand, you have those OCR buffers accessing the same value, for example, and it may be that some thread is getting this value for one reason, and another one is getting this for some other reason, and they simultaneously can try to read and write on the same value. It's already not part of the data structure. So we say this is external synchronization versus the internal synchronization of the data structure. And the external synchronization is actually pluggable, but currently it's implemented as lock. So we have this header. Inside header, we have lock, read-write lock, implemented on the off-heap, using concurrent solve, of course. And whoever is accessing for read is going to take the lock in shared mode, as a couple of readers can access simultaneously. And whoever is going to delete or to update or to write the value, the lock is going to be exclusive. Okay, this is in high level how we separate the synchronization of OAK. And I want to spare a little bit longer time on explaining backward scans. Okay, as I said, when you have concurrent skip list, in order to get, for example, you have something ordered in increasing time, okay, in timeline. But sometimes you may need to scan just analytically backward. How was it if I'm going backward in time? Or, for example, I have some analytics which may be interested in increasing age. For example, if you keep something about the persons and then in decreasing age. Okay, so with concurrent skip list, you will need to do log n steps each time you're going backward. Okay, so let's see. It's interesting. How do we resolve it with scans backward in OAK? Okay, so as I spoke about, we have those entries. The entries are half ordered. Okay, half of entries are already there because chunk was created from previous chunk, and they're ordered and they're linked together. When we add something new, okay, we already disturb this order. For example, if something was added after 40, then we can go here. If here is 41, 41 is pointing back to the 50. 50 is part of the ordered part where we do the binary search. Again, 50 may point to 52, then 54, and back to the 60. And this is how it looks after you add more entries. So, for example, let's say we need to scan from 63. Okay, we do binary search just on this part, on the ordered part of the array, and we find that the smallest key, which is the biggest among those smaller than 63, is 60. Okay, so our anchor is currently on 60. Okay, now you can travel from the ordered part to the unordered part and keep the stack of all keys that you see on the way. Okay, from 60, you know the next one is 63. Okay, and you may also see 66, but 66 is not that there was required to scan from. Okay, so I have in the stack 60, 63, then I can start scanning. I'm saying to the user, here's your scan backward. You first take 63, then you take 60. Okay, then I have empty stack. But what the best point is that I can move to the next anchor in just one step. Okay, I'm just moving from 60, sorry, to 50. Okay, and then I can traverse forward from 50, and again to have all the entries in the stack. Here we have 52, we have 53, so here this is the stack that I create. And then again I can return 54, 52, and 50 until I get to the next anchor, which is 40. So this is how I scan backward in O of 1 timing instead of O of log n timing, which is currently done in all of the data structure, concurrent data structure that we are aware of. Okay, and so here's the example of 41, and you think you can understand it. Okay, so here I'm going to give a few tips how we work with Off-heap and what we learned from working with Off-heap, and maybe it can help anyhow. Okay, so how usually Off-heap programs work with Off-heap. So it's used to use byte buffer and use the allocate direct method of byte buffer and given some capacity. Maybe you know that JVM also manages the Off-heap memory. How does it manage? It actually understands that there is a byte buffer object located in the on-heap, pointed to the off-heap with some address. And then when GC, Java collection, is going to deallocate this byte buffer object, it means that the last one who points to this off-heap memory. It hopes that this is the last one. Then it deallocates also the off-heap memory behind this direct byte buffer, okay, which is nice. But when we did implement it this way, we find that the GC works extremely slow. And we were required to give 3 times more memory than we can give with our ad hoc memory manager. And therefore, we opt to use our ad hoc memory manager because just until the GC got to deallocate all the byte buffers and the OS memory behind those byte buffers, just it takes too much. Okay, so usually as I'm contributor in HBase and in Druid, and I see how Off-heap is used there. Usually what we see how Off-heap is used, it's used for mutable data, it's just written once and that's all, and released usually by the end of the program generally running, okay, or when this Off-heap is not needed anymore, just released altogether. So usually data is immutable and allocate once, delete once without any usages, sophisticated usages internally. Okay, so how we do use it? First of all, we define blocks. Okay, blocks which are pretty big. In our case, we used 256 megabytes. Okay, and those blocks are going to be reused. So we have block pool. We allocate in the block per demand, but once some blocks are no longer in use, block is allocated with a single oak map instance. When this block is no longer when this instance is no longer live, therefore this block is no longer used, it's going to be returned to the block and can be given to someone else without the allocation and location again. Okay, because those blocks are big, we use slices on top of those blocks. What do we name slice? Is just part of the big block, actually related to some single location, for example, a key, a value, or whatever it's needed for you. Also, I can give you extra tip how we do work. When we work with those slices, we do not use duplicate or slice methods of byte buffer, because each of those, you maybe know, creates specific object and new object, and all those objects floating around is huge work and cost for GC. Okay, therefore, how we do use it, how do we access? We use absolute access anytime. We know for each slice, for which block is related, block ID. You see here it's written that the slices have, each slice have a reference. The reference is block ID, offset inside this block, and length. Okay, therefore, the position of each block is always 0. And we use absolute access. We actually calculate what do we need from this slice and read specifically this part of the block, which is part of slice. Okay. And we find, of course, much more beneficial because you don't, all those objects in the background, we didn't implement it that way with duplicated slice, are just nightmare. Okay, so how we do reuse, how you can reuse memory in Off-heap. Or sometimes, of course, you don't need it all to reuse. And sometimes you don't use concurrency. If you do need to reuse and you don't have concurrency, the life is much easier for you. What you can do is just to keep a free list of those slices which were deallocated. Once they are single threaded, there can be no concurrently someone else accessing to the same memory. So your life is actually easier. And so what you have is you can allocate through ++. You just have a current allocation of block. For example, till here it was allocated. Then you can just add something and then have a slice for whatever size you need, or you have free slices in the free list. Of course, it's preferred to be ordered by size. Therefore, you can easily find something that suits you size demand, or you can even collide two nearby slices to one if you need the bigger memory. Anyway, again, because it's single threaded, it's not shouldn't be a big problem. In case of concurrency, here I'm going to present a possible way that was implemented, though currently something else is implemented, but you may have a lock per slice. Here we have slices and locks near the slices. Each access in general is using this lock to say that I'm accessing this. And the problem is actually the problem and the solution is that those slices, those locks, which are actually in our case in headers, this part of memory cannot be reused, because there may be a thread accessing an old lock and trying to keep it. So you cannot release this lock and let it be used for some other cases. Okay, but again, we already rewrote this to the other solution, but it's a possible solution. And therefore, if you just lock the slice when it's going to be deleted, all the rest can see that the lock is already deleted. The slice itself is marked as deleted. The header is marked as deleted, and then you can just release this lock, and thread can continue. Understand that the memory it wanted to access is already obsolete. Okay. And again, I'm going to show you how we implement the Off-heap locks. Again, if we want something more sophisticated, it's a separate talk because it's too much sophisticated. So maybe I can give some other talk or write a blog about it, or you can wait for our next release and maybe next paper. Okay, so again, how do we work with Off-heap? In order to allocate, you already saw you use direct buffer, allocated from byte buffer using allocate direct memory. In order to write there something, just use put in, put long, whatever you need, and get in, get long in order to read. In order to create a concurrent swap, this is how we use concurrent swap. Here need to be an object, or in our case, because we give a direct address, we don't need object. Here is the byte buffer address and position where this lock is supposed to be. We have expected value and new value. And this is how in generally concurrent swap is written, and how to implement the lock using concurrent swap you can see in any literature. Okay, in JDK 11, we didn't transfer our org still to JDK 11, but we have a plan how to do it. But in general, if you want to, there are variable handles. Okay, to each element, to each object can be variable handle also of byte buffer, which can be allocated off heap. And then once you have this variable handle, you can use concurrent set operation of this variable handle, again, given the object and the offset. Okay, and this is how it should work with JDK 11. And here again, we can stop and see if there are any questions.
Yes, actually, there is a very interesting question from a colleague of mine. He asks if it is possible to persist a map on a disk without copying and reuse it after application restart, for example, by using map byte buffers.
Mm-hmm. We didn't use memory mapped files to be supported with memory mapped buffers, but in general, of course, you can. It will be just a bit of change to change the direct by buffer to be memory mapped buffer, but then those buffers as is, they are not so much maybe used. Why? Because what is memory mapped buffer? It's just something that is, as it is presented in memory, it's copied to the disk. Okay, in order to access the oak, you need this index on top of heap, right? Therefore, you know how it's ordered, where to look for some key. Otherwise, the keys and the values are written in the disk or in the off heap in some random order according to how it was inserted. So according to the timing, how it was inserted. Okay, what you can do, and we've thought about it, it's that you can create a magic number, some number, some order of bit that should not be, is not supposed to be written, because it's really some different combination of bits. And then you can find a start of key, for example, start of value. And then if you just search through the data, you can find like keys and values if you need, or you can use it in order to restore it in case of failure of energy, as you said. Yeah, it's possible to make the buffers what we use supported with the memory mapped file. It's not a problem. To create the correct recovery procedure, it's a bigger problem, but also doable. But currently, OG doesn't support writing to the disk and recovery from disk.
Well, thanks. I suppose, but I'm not sure that Andrei, who asked the question, tried to suggest his library that is used, for example, in Одноклассники caching solution that allows, for example, to read and to write from shared memory. And well, his question probably was about whether it is possible to restart application just to, for example, to kill the process and to restart it again, and without, for example, population from some source, but just start using it from shared memory.
Yes, I understand what you're talking about. You try to use it as inter-process communication, and currently, at least, OAK is not written as inter-process communication. It's single process with multiple threads. If you want it to be inter-process communication, it can, like as I think Andrei suggested, it can be done. But of course, it can be used as interprocess communication, just kill one process and then start from the other process. But this other process will need to rebuild the in-memory structure in order to just scan it or access in login or whatever. It will need to rebuild the oak from disk or from different process space, other space, or different process, other space. So yeah, it can be done, but just the process of recovery needs to be written. Like currently we don't have. If Andre wants to contribute to oak open source, we would be happy.
Okay, thanks. And as long as there are no questions from the chat, I would like to ask my own question about the API, the in-place API. You said that there is a possibility to use the set. If I wonder if it is possible to use entry set, not value set, but entry set. And
Of course.
Is remove operation supported in this set?
Yes.
If I
remove operation is supported in general in oak. And of course, you can. I don't understand really what remove operation you mean, but entry set is possible, and traverse iteration over entries is possible, of course. And any attempt to remove a value or key is also supported.
Well, let me give you a few details. For example, if I get the set and then I get an iterator from this set and I start iterating over the entries, and for example, during iteration, I decide to remove one entry. Is it possible to do it?
Within a iterator API, you do not have a possibility to remove, but you can remove. And the scan itself, the iteration is not atomic. Is not a snapshot. If you are asking about it, it's not that we are like presenting, giving you a point in time iterator, and then we may ensure that you are accessing just this snapshot. If there are concurrent deletion in time of the iteration, you may see or may not see the result of the remove. For example, if you have two threads, for example, one is removing some item and the other one is iterating, yeah? Then it depends on the concurrency of two operations when they access the removed element. So because snapshot is not atomic, scan is not snapshot in our case specifically, it's not an atomic scan. Therefore, there is an ambiguity there. Yeah, you can find this element there, or you may not find it there. But the possibility to remove exists. The interface to remove exists.
Okay, thank you.
I'm not sure if that's.
Okay, it answers
is
fine.
It clear?
Perfectly fine. Yeah. Yes,
okay.
Thank you. Let's proceed with the talk.
Okay. Let us continue. So I'm going to present you evaluation of oak, which was done in Amazon Cloud. We use the machine with 32 cores with 2 NUMA nodes. Our key size is 100 bytes and value size is 100. I'm sorry, value size is 1 kilobyte. Okay, we limit ourselves to 32 gigabyte of RAM, and we insert 12 gigabyte of data. But it was a small experiment, just to show you the concurrency and the throughput, which was the main interest of the evaluation, of this evaluation. Okay, so what do we see here? We have, first of all, we do a experiment with 3 data structure. One is, of course, oak, which is presented with blue line. One is, which is named here skip list on heap, is the concurrent skip list map of Java, which is represented here with orange line. And the last one is the green line. The green line is concurrent skip list map, which is just referencing its data in Off-heap. Okay, why we experiment with that is to show that Oak has advantages above the usage of Off-heap. Okay, it's not that, okay, so you just transfer to Off-heap, so that's all that you do. Okay, because you can see that the structure of Off-heap is different, the concurrency is different, therefore you will see the results. So let's look on the left side of the slide, and you see there a put. Ingestion only, put only throughput. On the y-axis, you have the throughput, kilo operation in seconds. And here, in general, we want to show the scalability. Therefore, here in the x-axis, you see increasing number of threads. Okay, so what do we see? With the increasing number of threads, more and more data is ingested, and the skip list is going to have flat throughput. Okay, it doesn't scale with increasing number of threads. Skip list Off-heap does increase, therefore the problem, we assume that the problem here was mostly with GC. But on top of the Off-heap skip list, you see that the Oak performs better anyway. Okay, let's look on the right side of the slide, and here you see gets only, and after, of course, ingestion of 12 gigabytes of data, and here we see interesting results again. So all that you see here is the get operation, which is 0 copy. Okay, and you see that it performs almost twice better. Also here you see, if you compare with in the puts, if you compare the throughput with big number of threads of concurrent skip list map and the Oak, we have almost twice better throughput. And back to the gets, to the right side with gets, you see that we have much better throughput, of course, with the 0 copy. And we see that on the when we compare with the skip list and with the Off-heap skip list, they all perform the same. But the dashed line, which is interesting, dashed line is all performing the copy in serializing the objects. Okay, when objects are deserialized, creating the objects, then you see performance which is almost comparable to the concurrent skip list itself. Okay, then let's come to the scanning. Okay, on the right side you see scanning in ascending order, like forward scan. Okay, and if we look on Oak performs poorly, little bit less than concurrent, not that poorly, but little bit less than concurrent skip list map of Java. And this, as I've said again, because of creation of Oak buffer any next step. Okay, but surprisingly, when we use stream iterator, it just doesn't create, it works completely the same, just doesn't create the buffers on the way. Here you see how much faster the performance is. Okay, and then coming to the descending scan, those are actually the backward scan that we're speaking about. Okay, and of course here we see that even not streaming sending scan of Oak performs much better than any of Off-heap. This is just because the concurrent skip list map of Java uses those log n steps backward. But even here, if we would use single Oak buffer to reference to any of them, for example, using Oak stream interface, then you're going to see even better performance. Okay, so far you have seen that it scales better, it has faster performance, and we are going to speak about real world deploy. Okay, so Oak was introduced is not yet inside Druid, but we are currently in process of integrating our Oak map inside Druid. Druid itself is a very popular open source real-time analytic database. It's a huge system used on multiple of nodes, multiple machines. And we are aiming just to change its internal index. Each node, each process has its internal index referencing the keys and values currently ingested in the real-time node of Druid. Okay, and we just changed, and the index that was implemented with concurrent skip list map of Java, and we changed that to be implemented with oak. Okay, and as a result, we named this result oak incremental index, oak and I in the power of 2, oak II. As a result, we see system level benchmark, actually Druid cluster running with oak inside, and we see decreasing memory consumption and much faster ingestion. And again, you are going to see here 3 players. Okay, first of all, you're going to see oak I in the power of 2, which is actually the Druid got in with oak inserted as its incremental index. And the second is the legacy solution of Druid themselves. And the last is also legacy code of Druid, where they have their internal off-heap index. Okay, also index where only values were written in the off-heap and keys not. This their solution, we just compared to them. We have a machine, another machine that we used in the previous experiment is already not Amazon Cloud. It's our machine with 12 cores, 24 hyper-threaded, and we have 36 gigabyte of RAM in general. So the storage is SSD, as we have here, writes through Druid to the disk. And the operation system is Red Hat 6. We run with Java 8. Okay, so what do we see here? Okay, we have a force of Perl of 3 players, as I said. We have oak written in blue. On-heap solution. This is Druid legacy currently running is the red one, and the pink one is the off-heap solution. Okay, so what do we see here? Here again, we see on the y-axis, we see throughput. Rows inserted per second. Rows are actually, you can say those are the values inserted because Druid represented table, therefore it speaks about rows. So in the concurrency line, in the x-axis, you see number of processes of Druid processes, Druid tasks, ingestion simultaneously data into the Druid. Okay, each of them has its separate incremental index. Okay, so here each incremental index is oak, but running with one actually thread or one process. Okay, so what do we see here? When we use on-heap solution, it stops after we're working with 4 tasks, 4 processes, hitting 39 gigabyte of data. Off-heap solution works faster with a little bit better throughput and hits 33 gigabytes and then stops. And O can continue till the end. Pay attention that entire data, entire memory what we have here is 46 gigabyte. It's what you have on the machine. And the oak actually scales till 45.5 gigabyte of data. Okay, and with much higher throughput. Okay, it's not already oak, it's oak Druid based on oak, so it includes much more code than just oak itself. Okay, so this was an example, and I think I went through all the promises that I had. Okay, so just quickly speaking about how to use oak, if you would like to. So here's again the link to the open source. You can clone it for yourself. You will need to create serializer and deserializer and calculate size as we speak for your keys and for your values. You will need also to create the comparator for your keys, as we don't know what your keys are. We don't know how to compare it. Again, for the primitives, you have all those things already existing, and the builder need to be created in order to create oak map, and then just use builder build method. You need to decide where you would like to use zero copy API or not, and just use it. And in any problem I would like to support, here's my email. You are welcome to write to me. When do you want to use oak? It may be interesting already if you are using more than 4-5 gigabyte of data, because with all of it you will already see a better GC performance. Okay, if you experience GC pauses or any GC related issues, or it takes too much time or too much memory, it's also a flag to consider using Oak. Again, we want to share with you what we are implementing now Oak hash. So if you want not ordered map, it's going to be soon available. And you can also, of course, again, contact me. Any problems, anything unknown, just contact me. Okay, so to summarize the lecture that we had, I talked about Oak. Oak is first, as well as we know, concurrent, very well scalable off-heap data structure that uses the data itself. It reuses the same data again and again. We have suggesting novel zero copy API in order not to copy and create objects anytime. We have concurrent algorithm. We have fast two-way scans. And we are lean in the metadata. Our metadata takes just 2.5% of the raw data. It's almost twice faster than concurrent skipless map of Java. It's almost integrated into Druid, and it's open source solution. Here I have all. If you have more questions, I would like to answer.
Okay, thanks a lot for such an interesting talk. Actually, we are running out of time, but there is a couple of seconds, I would say, to ask one question. Anton Vinogradov asks, what if item is removed from the off-heap space and there is an empty space between some entries, and what should be done with this space if there is any support for defragmentation of this area?
Yeah, currently we do not support any reallocation in order to fight fragmentation. But if this size is suitable for any other future allocation, we are going to reallocate it to future usages. But if like no one else asks for such size and everyone asks for a bigger size, then yeah, it's going to be empty space.
Okay, well, we ran out of time, so please be sure to join our Zoom chat. We're going to be there momentarily, and thanks a lot for your attention, and thanks a lot to Anastasia for such a brilliant talk.
Yeah,
Thank you very much.
Yeah, hello everybody. I'm coming to you to say that your talk is almost ended. So that was an incredible talk. Your feelings, Anastasia, after this talk? Have you covered everything you wanted, or
I
there is
think
something?
so. I hope so.
Yeah, because
I
there
hope
is.
It was understandable.
Yeah, it was quite understandable. There is very tricky question that waits you to the Zoom session. I think there is in the chat about memory manager. So you will have a huge.
Okay.
You have to prepare a very huge answer for that, because this will take a lot of time. Yeah, I warned you before. So since we have like 40 seconds probably left, can you probably briefly remind, like, give an intuition what is going to update it in this org in the future? Some updates.
We have recently just recently have a release, a big release with many fixes and updates and performance wise, and we are currently working Oak hash. It's going to be ready soon, and after we have the Oak hash, we are going to introduce the new memory management. Probably that's what the questions are about. But yeah, it's not going to be really soon, but it's going to be in the near seeable future.
Okay, great. Thank you very much for the talk, Anastasia. Timur, thank you very much for your expertise.